Hi, welcome to the class. This is Chandrakant Mishra here. Today we'll discuss the network theory, and this is the topics which is indispensable subjects for electronics communications, electrical and instrumentation engineering branch. This is a foundation course to move forward to explore the other topics of the branches. Take the gate weightage. It is 10 to 12% of the marks, keeps on coming each and every year, and other engineering competitive exam substantial questions you will find in those exams. The most important thing is to understand and apply the concept in the further topics like analog electronics, analysis of DC analysis, AC analysis of amplifier circuits, digital circuits, communication circuits. So let's move with the basics of the network theory. So network basics, you know that electric current involves the electric charge, and the quantity of charge is the 1.602 into 10 to the power minus 19 coulomb. Charge in a system is always conserved, right? And the charge exists either integral multiple of positive E or negative E. And the basic relations: current I equal to dq upon dt, and if you want to find the Q, total charge passed over a time, so integrate minus infinity to the final time, starting point to the ending point, I dt. 1 ampere of current is the flow of 1 upon 1.602 into 10 to the power minus 19, which is equal to 6.24 into 10 to the power 18 electrons per second. These things came from the relation this. Other basic relations are potential V equal to rate of change of work done with respect to the charge, where W is the energy, V is the potential, and Q is the charge. Or you can write W is equal to integrations minus infinity to the final value of Q, then V dq, and then power P is equal to rate of change of work done or energy, time rate of change of work done or energy. If you little bit manipulate, dw upon dq into dq upon dt, which is this term is your V, this term is your I, so V equal to VI. Next we'll discuss the conventions for an electrical element. This is very much important. You should give particular attention to here, because it helps to move forward in the network theory. Is any element, whether it is a voltage source, current source, capacitors, inductors, or any abstract elements, resistors, anything like that. So current, I'll force a current I, so potential will be the VC. Current entering the terminal becomes positive, and current leaving this terminal become negative, and the current entering the terminals become positive, and this is voltage with where the current enters, it becomes positive. This is called the positive conventions for electrical element, right? So you should remember positive current and positive voltage. This is I positive, this is V. Okay, so this is drawn in the positive axis, that is, you can call the first quadrant. This is the first quadrant. So this is the conventions for positive current and positive voltage. For example, if I ask you, say resistors, let's say 10 ohm, let's say current flows through the 2 ampere. What is the value of V, and what is the value of this V1? According to the conventions, V will be equal to 10 into 2, that is 20 volt, and the V1 will be the minus of V, which is minus 20 volt. Then we'll move to the power convention. Power convention is the same. You just take the reference of positive voltage and positive current entering through the terminal, and this terminal become positive, and this V. You calculate the V, instantaneous power or average power, VI. Just multiply positive current and positive voltage, VI. And if P is positive, power is being absorbed. Okay, absorbed by element, a random element, this element E. If PE comes out to be negative, power being delivered by the element. We'll discuss more in the later examples. These are the conventions. You are expected to know all these things. Next we'll move to the passive circuit elements, their governing relations. First we'll discuss the resistors, and the physical quantity is the resistance, and unit is ohm. So governing equations are V equal to IR and I equal to V by R. See the conventions first. Okay, then instantaneous power, P equal to VI I square R V square by R. Average power is very simple. Average power calculations, limit t tends to infinity, 1 upon t, and over a period, power, instantaneous power, and energy consumed, W equal to minus infinity, that is initial time, to final time, P dt. Because it is a resistor, so it always consumes power. Next we will discuss the capacitors. Measured quantity is capacitance and unit is farad, so current and voltage. See, the every time I write the same conventions. So for the capacitors, I is equal to C rate of change of D, then your V equal to 1 upon C integration minus infinity to final time, and then I dt. So instantaneous power, P will be the V into I, which is equal to V C dV upon dt. Okay, and you can find the energy, total energy, which is equal to minus infinity to final time P dt. Ultimately, by putting all these relations and the final value of voltage, you will find half C V square. What is the V? V is the final values of the capacitors at time TF, final time. This is called the final value of capacitor, how much capacitor has been charged at the time TF, and you will get the this energy, half C V square. Next, inductor, physical quantity inductance and unit Henry. Same way, write the elements I, V equal to L di upon dt, and I equal to 1 upon L in minus infinity to final time TF, and your V dt. These are the basic relations you should always know. Then instantaneous power, you will have L I di upon dt. Same way you can find the energy stored at the final time when the final current flows. It will be half by simply integrations L I square. I is the final current flowing through the inductor. Current cannot be changed instantaneously, can't be changed instantaneously through ideal. Current cannot be changed instantaneously through an ideal inductors. I mean ideal capacitors. Voltage across the ideal capacitor cannot be changed instantaneously. These 2 points are very important. Point 1. Next we will discuss the energy source. Energy source are 2 types. You will find one is the independent, which means source is completely independent of the other circuit variable, and dependent, the values of the source depends on the variables of circuit elements, either current or voltage. Typical independent sources are, it will write a circle either V or I. Both tells either AC or DC. But when you have the source like this, it indicates a ideal battery, right? So they are represented like this. Dependent sources. These sources are dependent on the values of the current or voltage of some other elements in the circuit. These sources are represented by diamond shaped symbols. Always you will find the symbols as a diamond shaped. That means it is a dependent source. There are the 4 because we have 2 variables, either it can be voltage or current. We have all total 4 dependent sources. Voltage controlled voltage source. The source is a voltage source. It is controlled by the voltage across the some element in the networks. Then voltage controlled current source. Voltage controlled current source. Source is a current source. It is controlled by the voltage across the some element in the circuit. Then current controlled voltage source, that is source is a voltage source. It is controlled by the current through some element in the circuit. 4. Current controlled current source, that is this is a current source and it is controlled by the current through an element in the network. So the representations are like this. So always remember these dependent sources are linearly dependent, not any square. You can just square root law like this. So voltage controlled voltage source, so I'll write a constant K and V. So it indicates a voltage source controlled by a voltage across some element in the networks. So this belongs to this. And what about this voltage controlled current source? Same diamond shape first of all. Then this is a current because current source symbol. Then voltage control, so K1V. Then another one is a current controlled voltage source. So source is a voltage, current through another element. And this one is your current controlled current source. Okay, so current controlled, and this is the current source, and this is controlled by the values is controlled by the current source. So this K, K1, K2, K3 are constants. We will not deal with the dependent source like K2 I square or I over root 2 K3, not. So as all the circuits we deal with the linear circuits, so we will always deal with the linear dependent sources. And analysis part we will discuss later with example. Next we will go for the KVL and KCL. Kirchhoff's voltage law. It tells that the algebraic sum of all branch voltages around any closed loop of a network is 0 at all instant of time. That is, in short, algebraic sum of all voltage around the closed loop is equal to 0. So important point here, while applying KVL, traversing from negative terminal to positive terminal, a rise in potential, hence a positive voltage, and traversing from positive to negative, a fall in potential or negative sign for the voltage. Here with an example. I'll assume a direction of the current. Let's say this is the direction of current. We know that when the current enters the terminals, it becomes positive, this becomes negative, and this becomes positive, this negative, this becomes positive, and this becomes negative, and you have already the terminal marked for the sources. So you traverse. Anyway, you can traverse. I will traverse this way, right? So I'll write the equations. I'll traverse, start from here. While traversing, I found that there is a V1. So I am traversing from negative terminal to the positive terminal. So rise in potentials. So I'll write plus V1. Similarly, traversing from negative to positive terminal here, R3 across R3. So I'll write this potential is the current, because we have studied voltage across the resistors. So current I into R3. Similarly, plus I R2 plus I R1. Then for this source V2, I am traversing from positive terminal to negative terminal. So fall of potential. So I'll have a negative sign, V2 equal to 0. So if you want to arrange, I clear? So example, what is the values of V? So as this terminal is open, so no current flows, so voltage across is the 0 volt. So simply use this potential V as a closed loop. Assume that it is a closed loop, so the potential will appear here V. So you apply the KVL here. So traverse this way. So V plus 0, because no current flows, so current is 0. Then traversing from negative to positive, plus 6 volt, then plus 6 volt, then this will be the minus 5 volt, this will be the minus 2 volt, then plus 3 volt, okay, equal to 0. So your V will be the how much? Just add together, so minus 2 volt. Suppose somebody asks you what is the values of this V1. So simply V1 will be the negative of V, which is minus of minus. Understand these small things matters a lot during the exam. Next we will move to the KCL, Kirchhoff's current law. It tells that the algebraic sum of the current entering a node or a closed boundary is 0. That is summation all current at any node or closed boundary. This is a node. This is current I1, current I2, I3, I4, and whatever the closed boundaries, something like this. This is called the closed boundary. You can take any directions, that is a sign. Once it is entering, I will take the positive sign and leaving negative sign. So I1 plus I4 plus I3 minus I2 equal to 0 for this case, and for this case I1 plus I2 plus I3 minus I4 minus I5 equal to 0. So summarizing, KVL, conservation of energy, and KCL is the result of conservation of charge. Okay. Next is the elements in series, parallel, and these things I consider the trivial ones, and if people are know all these things, like resistors are in the series, they are together, the resistors are in the parallel, so equivalent resistance is the 1 upon R1 plus 1 upon R2, like this. Okay. Similarly, the inductor, they are non-coupled, same follows equivalent L1 plus L2, equivalent is 1 upon L equal to 1 upon L1 plus 1 upon L2, like goes on. And you will consider for the capacitors, if capacitors are in the series, so their equivalent is just reverse of that, 1 upon C1 plus 1 upon C2. If they are in the parallel, so C equal to C1 plus C2, C3, like this. Next we'll discuss the Y delta or star delta and delta Y or delta star transformations, where here we have A, B and C, the impedance of delta structure, delta networks, and alpha, beta and gamma is the impedance of star structure or star network. Alpha will be simply A B upon A plus B plus C. Beta will be the B C upon A plus B plus C. Very simple. And gamma will be the A C upon A plus B plus C. You will find A very simple. Just try to, if all the elements are equal, A equal to B equal to C, let's say Z delta, gamma equal to beta, alpha equal to ZY. So you'll easily find that using these relations, Z delta, that is impedance of delta, is 3 times impedance of Y. So short questions, it will come in the exam. Clear? Next we'll discuss the node analysis method and the mesh analysis or loop analysis method. So number of independent equations are the n-1 for the node analysis, and the mesh analysis the b minus n plus 1. That means minimum numbers of equations should be this. What is the bn? B is the number of branches in the network, n is the number of nodes. So accordingly you can use which one will be the easier you will be using. Sometimes you require the application of the both node analysis and mesh analysis, wherever you will find the super node or super mesh in the networks. So it is not specifically you need to read all these things, because after all it required solving the questions. They don't ask the method you use, whether node analysis or mesh analysis, whether there is a super node or super mesh. So ultimately you will be using a lot of different techniques as and when you study the network theory. Then you'll, after these basics chapters, you will find the topics of network theory like network theorems. You will be using all these theorems to find out the circuit variables. So the highlighted point or the critical point here, the whether you go for the node analysis or mesh analysis, it depends upon the which one is the lesser number of equation to solve, right? So we'll discuss the some of the examples, also get questions. Let us start with the example 1. The value of V0 is. So how to do this? First of all, you check if there is a dependent source, that is a voltage dependent current source, and there is a voltage source here, just connecting the two nodes. So you need to mark this point as this is your V1 and this is your V2, right? Then you apply the this side, you apply the KCL. So when the current goes here, so 5 amperes, understand this current 5 amperes goes, so it will goes here, it will goes here, and it is goes here. So 5 amperes is equal to, obviously make it ground, so V1 upon 10 plus V2 upon 5, then plus V0 upon 2. V0 is same as the V1, or you can say here V0. So just modified V0. 10 upon 6 V0 plus V2 by 5. What is this 10 volt? V2 minus V0 is equal to your 10 volt. Equation 2. So your V2 is equal to 10 plus V0. Equation 3. Using equation 3 in equation 1, we have 6 V0 plus 2 into 10 plus V0 equal to 50. So you have 8 V0 is equal to, because 6 to 8, so 20, so which is equal to 30. So V0 is equal to 30 upon 8, that is clear, 3.75 volt. Next example, what is the value of V0? As you know, already you will find the current. Let's give the directions current I. So what is the current? So use the KVL. So I will traverse this way, plus 2, then plus 2 into I, plus 2 into I, minus 12 equal to 0. So 4I equal to 10. So I will get the I equal to 2.5 ampere. Clear? So now I need to find the V0. So V0 I will be using the in between this, traversing direction this. So I will traverse this way, negative to positive, so positive V0, then this way negative to positive, so positive 2 volt, then negative to positive, then positive 2 into current I equal to 0. So V0 equal to 2 minus 2 minus 2 into 2.5, that is minus 7 volt. Clear? So is the example 3. What is the power delivered by the dependent source in watt? So dependent source is here, that is V1 upon 5. So it is in fact not dependent source, because voltage is fixed. This voltage is not varying. So this current is always 20 upon 5, that is 4 ampere. That means how much power is being delivered by this source, right? So current is the this. So we need to find this voltage. So then only we can find the power. V into I. Apply the KCL here. So 20 minus V upon 5. See here, this is the 20 volt here, this is the V. So 20 minus 5 V upon 5 is the this current, and this is the also inward current, so plus, and this current will goes downward, which is equal to V upon 5. So manipulate. So 20 minus V, 20 equal to V plus 2V equal to 40, 2V equal to 40, or V equal to 20 volt, right? So here we have 20 volt, and here we have the 4 ampere. Now you go to your conventions. Okay, we have current of here 4 ampere direction, and we have voltage of how much? 20 volt. So power is equal to, let's say this is your V and this is your I. So power is equal to V into I. By conventions, current entering the terminal is the positive current I, and the terminal where the current enters becomes positive terminal, so positive voltage. But here, what is the value of V here? V and 20 volt are opposite, so V equal to minus 20, and I same directions, is 4 amps, that is minus 80 watt. So negative sign indicates that the power is being delivered. In fact, they have asked the power delivered, so power delivered is the 80 watt. Let us try this example. What is the power delivered by 3 ampere source? So we need to find the V. So V will be the 10 minus 3 into 2, that is 4 volt. So by power conventions, P equal to VI, both are in the conventional directions. So V is equal to 4 and that is just 3, that is 12 watt. But this is observing, but they have asked the power delivered by the 3 ampere source. So power delivered will be the negative 12 watt. In fact, power delivered of negative 12 watt means positive 12 watt being absorbed by the 3 ohm source. Clear? This is again 2011 questions. In the circuit shown below, the power supplied by the voltage source is. So obviously you need to find the current I, then V equal to I the supplied power. So you know the 2 amps here, 1 amps here, 2 amps here, so we have 3 amps. So here the you will have 3 plus I. Okay, 3 plus I, so here you will have the 2 plus I, right? So 2 plus I, so you can use the KVL around the larger loop. So 10 minus 3 plus I, this way, minus 3 plus I, okay, into 2, because 1 ohm here, 1 ohm here, then minus 2 into 2 plus I, right, equal to 0. So 10 minus 6 minus 2I minus 4 and minus 2I equal to 0. So 4I equal to, which implies I equal to 0. That means, so power delivered is the 0 into 10, that is 0 watt. This is a GATE 2012 questions. If VA minus VB equal to 6 volt, then VC minus VD is given by. So they have been given VA minus VB 6 volt. So obviously if VA minus VB is the 6, that is this voltage is your 6 volt. So the current will be the 6 upon 2, that is 3 ampere. This is 2 ohm, right? So obviously this current, whatever going here, wherever it goes like this, ultimately the return path is only 1. Yes or no? So that means you have 3 amperes here, right? So that 3 amperes and your another 2 amperes will flows through this node. This is coming 2 amperes, this is 3 amperes, so it will have the 5 ampere. So they have asked VC minus VD. Obviously this is your VD, that is VD minus VC equal to 5 into 1, that is 5 volt. But they are asked, see the difference, VC minus VD. So VC minus VD will be the minus 5 volt. Very simple questions, and it was asked in the 2 mark section. Next, these questions have here this year with the 2 mark sections. Consider the network shown below with R1 1 ohm, R2 2 ohm, R3 3 ohm. The network is connected to a constant voltage source of 11 volt. The magnitude of the current in amperes accurate to 2 decimal places through the source is. So first of all, this is R1, this is R1. Up to this they have symmetric path. Now see up to this node, what this is, R2, R3, R1. When this node we have seen, this is R2, R3 and R1. So this of the equipotential, that means here whatever the potential will be, the here will be the same potentials, because they see the same path. And similarly if you see this is also seeing the same path here. Current bifurcate here, you see that R2, R3, R1. Here also see to the R2, R3, R1. Here will be V2, here will be V2. So as you know the equipotentials, so it will be clubbed together. So ultimately you will have the R1, this node V2 is a V2, then at the V2 this R2 no current flows, then R1, R1, R3, R3, R1, R1, R3, R3, then again R1, R1, 11 volt. So R1 is your 0.5, that is 1 ohm 1 ohm. So equivalent you will get the 0.5 ohm. This is R1, so equivalent 0.5. So this is the R1 R1 and R3 R3. So you will have the 0.5 parallel, R3 is the, so 1.5. So equivalently you will have like this 0.5, 0.5 into 1.5, 0.5 into 1.5 upon 2, that is your 0.5 into 0.75 upon 2, that is 0.375 and 0.5, and connected to voltage source of 11 volt. So ultimately you will find the current I is equal to 11 upon 1.375. So it will become 8 ampere. So next final questions of this lecture is the GATE 2016. In the circuit shown in the figures, the magnitude of the current in amperes through the R2. You need to find this current magnitude or R2. Let's say this current whatever I. Node analysis. let it be V, right? So 60 minus V upon 5, this current, and this current, how much it is coming? Plus 0.04 Vx, and then this current, which is equal to V upon 3, V minus 0, of course, upon 8. So you will get, you multiply both side 40, 8 this side 8, 60 minus V. When you multiply 40, you will have 1.6 Vx and 5 V. But what is the Vx? So Vx, by potential division, you can find Vx equal to 5, 3 plus 5 into V. So Vx equal to 5V upon 8, which is equal to 13V minus 1.6 into 5V upon 8. So how much it is coming? 13V minus V, which is 12V. So your V will be the 480 upon 12, 40 volt, and the current will be the, so V upon 8, that is 40 upon 8, 5 ampere. This is your, okay. This is all about the basics of your network theory. I have covered up the conceptual things, then examples, then typical gate questions. Now rest lies on you to explore the things, solve the questions, then go back to your conceptual things, then again apply in solving the problems. Then in this coursive way you must follow. Thanks for watching my video.